Okay, right. So for context, I was supposed to give a talk at the Simmons Institute a week ago, and then my flight got canceled, and I prepared these nice slides, and so I'm going to present it to you all. And this is very informal. Feel free to ask silly questions, even serious ones. So basically, what I thought I was going to talk about was it just so happens that 10 years ago, Austin gave this other talk where he included this nice slide that showed how they were building the surface code constructions back then, or at least how he was. It's sort of hard to summarize the state of a field, but here we have someone who has attempted to do that back then, and I will treat this as the God-given truth for what people were doing, even though I know that's not quite right. Also, the Martinez group, like Julian's paper on the rep code, also appeared in 2014. So it seems like a kind of fortuitous time to do the comparison too. But I'll start with like the surface code comparisons because that's what I'm the most familiar with. So back in 2014, the way that they encoded logical qubits is very different from how we do it now. So right now we make like boxes and we put our qubits inside the boxes. Okay, we cut out a box. There's like red and or X and Z type boundaries alternating. Logical qubit is inside the box. Back then, they had like an open ocean of surface code and they would punch holes in it. And the qubits were loops around the holes and lines between the holes. So this is not very space efficient because your holes have to have a separation D between them. And the holes also have to have a perimeter that's at least D. And because they're using 2 holes per qubit, and also because they're using the unrotated surface code instead of the rotated surface code, it was like 12.5 D squared physical qubits per logical qubit, where now with the basic lattice surgery setup, it's 2D squared.
12.
Yeah, it used to be 12. Actually, one of the great things about this Austin talk is Austin is very laser focused on like, we need to get this done. And so people are like, isn't that extremely expensive? And he's like, yes. And also we need to do it. So I don't know. He has a level of focus that I like. And I also like reducing that by a factor of 10 in terms of the requirements. So the basic lattice surgery logical qubits are already 6 times cheaper just from sort of a better layout. It's especially weird looking back in hindsight because lattice surgery is so much easier to explain to people now compared to braiding. But back then, the belief was sort of the opposite. They knew a few things about lattice surgery, but I mean, Austin thought braiding was simpler. It took a while before we kind of came around. And now I can't imagine going back to braiding. Doesn't that sound awful?
I mean, I feel like I grew up in the glorious lattice surgery future.
Yeah.
So like what about braiding made it seem simpler? Was this just like a lack of vocabulary for like T-junctions are nice? Or was this like a people were scared of Majoranas or like what?
I think it was just familiarity. People had figured out the braiding and they hadn't figured out the lattice surgery yet. Like they knew how to do like
straight
this
novelty.
Yeah, I think it was just they knew how to do the C-naught gate with lattice surgery, but they didn't know how to do anything else.
The language of braiding is pretty easy once you have like the notion of things. Laying out is different, but
Yeah.
we use the rule of the braiding.
Sometimes you say things that make it really obvious to me that you're a physicist.
Yeah, this I was about to say
about to look at these diagrams and I'm going to immediately
it probably actually does somewhat come from physics, where people thought of these things as little particles moving around and braiding.
And you understand topological protection. This is why I think this idea comes from. Whereas like lattice surgery, it's really harder to see it.
Yeah, that's fascinating. Again, and this might be like a bias of how I learned these concepts, but I have like exactly the opposite intuition.
I agree with Matt. Like I agree, a braid is sort of a topologically non-local thing. It's hard to perturb it, but so is a junction where you've attached the pipes to each other. Like they don't want to disconnect. Also, when you're looking at a diagram, recognizing a junction is much easier than recognizing a linkage, especially when the linkages start getting all tangled up and computations get optimized.
I think like if you are in the, you just show the like the Mariana or like the wire, right?
Oh yeah. All right. Well, I have some figures later on, and you tell me which ones look simpler. Also, we also know some other tricks now where so this is a rotated surface code patch, and this is like the world's simplest parity check code. And you kind of like jam one inside the other. So you have one enormous parity check that you measure with lattice surgery. And it turns out that this gives you pretty big benefits, like a factor of 2 reduction on top of the factor of 6 we already had, a little bit more if you make it a little more complicated. So with the exact same assumptions as they used in 2014, we can get 10 times reduction in space. All right, so here we have the CNOT gate 2014 version versus 2024 version. Actually, you'll notice the paper that I'm citing is from 2011. This kind of speaks to my point of like they sort of knew about it, but they hadn't figured out all the details. Yeah, so this one on the left, you have the 2 qubits are sort of the 2 pairs of red poles. And then this blue thing that you're wrapping around it is what's achieving the CNOT gate. So Alexi,
Yeah.
perhaps you'd like to describe why this is a CNOT gate,
I mean,
because it's so obvious.
You see the loop, right? So
Yeah.
you see that there is like a topological thing that is moving around. Whereas like on the left, it's just
It is
I
true
just
that you
see
can tell
cube.
something is happening, but can you tell what is happening?
I would have to think more like
Yeah.
know a bit better about like the representation to see what get it doing, but I see that it's doing something that is not the identity by just looking at the loops.
Yeah.
And I see that there is like I don't know. I see I more than this maybe, but like on the left, I just see cube. I'm sorry, I just see like
Think
block.
about the one on the left.
Yeah, but you see,
It
like,
is- I have
you know,
drawn
it's a
these,
gate.
uh,
There is just like
Incidentally, normally we draw these with more spaced out
Yeah.
things so that you can tell the connections, but I've very intentionally made these to scale where if you literally put them next to each other, I mean, I know that these are processes that happen over time, that they would be about these size. And I'm not using a perspective projection, I'm using a parallel projection so that actually it should be like area corresponds to size. But yeah, they used to do this braiding thing. The qubits are maybe like the reason that the qubits are so high here is maybe more to do with the representation with 2 holes instead of the gate itself. That'll be maybe a common theme throughout this is that the qubit count is kind of awful, but you can also see that the time has gone down from this one to this one. And that's because, again, like in time, so incidentally, these diagrams, the vertical direction is time. You don't really need to understand the details of them. You just need to like look at the pretty pictures, but the vertical direction is time.
What is the height of the little blocks in the braiding diagrams?
Those are d/4. The reason that I picked d/4 as the size of the square is because if you want to make a hole that is symmetric and its perimeter is d, you want the d/4 diameter of that hole. And so that sort of makes a natural unit to make these diagrams with.
Cool.
Whereas here the unit is d for where the divisions are showing up.
You only need d/4 width on all these like flat regions.
That's correct. Although you may notice that these cubes are not really cubes. They're like sort of rectangular. They're not, there's some aspect ratio. That's because one is using the unrotated surface code, one is using the rotated surface code, and that causes a factor of 2 that I'm accounting for by stretching it a little bit. Yeah, so the reason this is 2.5D rounds is really to do with the fact that this blue top, the time until you can have another blue thing is you have the spacing there and you have the spacing there. But yeah, the CNOT gate, honestly, this is the one that there's maybe been the least improvement. It's pretty close, except for the space, but again, that's more of a memory thing.
So I have this sort of intuition that like CNOT gates are not really natural in lattice surgery. Are they not really natural in braiding either? Like this thing has to kind of bend in 2 directions and it seems to be kind of more complicated than whatever the basicest thing I could imagine should just be like a blue donut. Yeah.
Yeah, it definitely feels more natural in braiding than it does in lattice surgery. Like in lattice surgery, the building block really is pair measurement between 2 pipes, or more generally, like the junction.
Yeah.
The equivalent of the junction in the braiding diagrams is the linkage, where a ring links with another ring. So here you have like a ring below and a ring above, like the bottom of a U and the top of an O. And this is linking with both of them. And also it's linking with this sort of ring that we don't see the top and bottom of over here. So you could say that the natural thing in the braiding diagram is whether a ring is linked or not with another ring of the opposite color. It's a lot harder to see that directly because that's a global property whether 2 things are linked. You can't tell by just looking locally. Yeah. Here we have the Hadamard gate. So the funny thing about the one in 2014, is that it's basically turning it into a lattice surgery patch temporarily in order to perform the Hadamard, to perform the domain wall, where you perform transversal Hadamards across the patch, and then it converts back out and then fixes the fact that things are in the wrong spots by moving them. Whereas the one on the right, it's actually a very similar vibe, where you want to do this transversal Hadamard in order to get the bases correct, and also you want to rotate things in order to make the orientation correct. So here, the basis change looks very different, and then you have the rotation. Here, this bottom block is basically the rotation, and then you have the basis change, and then we're in the wrong spot, so we shift over back to the left and go up. Really, I would say it doesn't make sense to think of Hadamard as similar to CNOT as the basic gate. The basic gate here is like the domain wall and the patch rotation and the shift over by one. And in context, you'll always pick whatever works best from that subset, because you often don't need all three.
Was the construction on the left already understood as transform into a lattice surgery qubit? Like this is post 2011. So they
don't
talked about it that way, or?
In Austin's 2012 paper, he describes this, and I don't think he was thinking about it that way. He was thinking about it more as, I need to fence this off from the rest of the area so I can do something weird to it. So he would introduce this wall to fence it off and then shrink it down. And yeah, I don't think that's how they were thinking about it, but you have to ask Austin to be sure.
So if the sort of most primitive gate on the right or gates is like this domain wall and the shift and rotation.
Yep.
Then like, do people, I guess, think about compiling algorithms in that language? And why don't we use that as the sort of native gate counts?
I think we should do that, and I think mostly people don't because they come at it from the circuit picture. And in the circuit picture, there's not really a way to distinguish, like the patch rotation just doesn't show up at all in the circuit picture because there's no notion of the orientation of the qubit. But becomes extremely important once you get into the last surgery picture. So I think that kind of stuff will have to percolate up the stack a little bit. It's not clear to me at how high up the stack it should go. Like when the person is describing a chemistry algorithm, how much should they think about my qubit is right-handed or left-handed or whatever. Then we have the S gate, which is the last Clifford that people typically use to get the complete set of Cliffords. This is the one that's had the most improvement because back in 2014, they didn't know any way to do an S gate except by distilling an S state and then consuming it like T-gate style, except because it's a stabilizer state, you can duplicate it while you consume it. So it sticks around, it catalyzes.
Here I see a CNOT Hadamard, a CNOT or Hadamard.
That's right. That's exactly right. So it turns out if you have an S state, I believe it's the one where the Hadamard is happening on the qubit, and you do this pattern of CNOT Hadamard, CNOT Hadamard, the S state is preserved and you kick back an S phase onto the other qubit.
Oh boy.
Actually, the very simple thing you can do to improve this is you can just remove the second Hadamard because Hadamard on an S state is equivalent to, I believe, a Z on the S state, and Z is super cheap.
Mhm.
On the right here, we have a much smaller construction, which is based on, I think in 2017 or 2018, Ben Brown figured out in a lattice surgery patch, you can like pull out these defects from the corners, they call twist defects, and braid those in order to achieve the S gate. And then last year, I figured out a particularly compact way to do that, which gives us this like, oh, you just have this little box on the side that has this half-size thing above it or below it, and that achieves it. So this one has been improved enormously, but not as much as the T-gate has been improved. So, Alexei, here on the left, you'll notice a very simple linkage construction, which obviously corresponds to not the identity.
But here, like this is like a lot. Like you can decompose this, right? This is not just Is this a distillation process or something along this line, or is it just like
It's-
injection?
The bottom bit is preparing the 15 qubit Reed-Muller code.
Okay, so this is
state.
a 50 to 1
Yeah,
distillation.
that's
So
right.
it's of course it's going to be more complicated, but like if you take the bit, it looks like there is just C naught everywhere type thing.
Yeah, I don't have a picture of the lattice surgery version of this. This is not the lattice surgery version of this. This is cultivation, but the lattice surgery version of this factory, when I look at it, I can tell what it's doing. Like I can see the pair measurement or the parity measurements. With this linkage construction, like I have a very hard time picturing even where the rings are, like, and whether or not they're going through each other. Like you can kind of tell that there are rings.
Yeah.
There's a bunch of red poles and
But I think you want to represent this at this point. You represent this with the C naught, like the actual circuit, right? And here it's natural because
well, the way that they made these was that they started with a very simple representation where they brought C naughts in from an encoding circuit, and then they applied identities to shrink it. Like you topologically deform it, you apply something they call bridge compression, all kinds of stuff, and then you get this tangled mess. And it's very, very hard if I gave you this tangled mess for you to figure out
okay,
what it's doing.
On the other hand, I support Alexi's initial thing. I mean, you look at that and you see that it is doing something topologically non-trivial.
That's right. It is not the
Yeah,
identity.
see that. I said it's not the identity.
Yeah, yeah.
And
but
you
this-
said there is a bunch of qubits, right? And
Yeah.
if you count,
I do also see that it's
15.
very big.
Yeah.
yeah,
Hey,
so this,
Greg,
yeah, Emma.
I'm just curious if the limiting error mechanisms are the same like power in the distance of the code here. I guess, since the like T-state protocols here are very different, maybe in cultivation you have like D to some low power limit of the target infidelity, and I'm wondering if it's the same here for the braiding case that you're showing.
It is the case that you have like sort of similar lambda, where if you have a similar error rate, noise rate, then growing the code distance by 2 should give you like a factor of 10 reduction, assuming a noise strength of 1e minus 3. Like the lambda is pretty similar, I think, between braiding and lattice surgery. So that part's similar. What is very different here is this is before Lee injection. This is before people realized your magic state injection, you should post-select it.
Uh-huh.
Like the magic state injections here are actually these like kind of pointy bits at the top, which are a little hard to see.
Yeah.
They're happening after the code is prepared, and they're happening in line. So they all have to succeed simultaneously in this layout.
Oh.
And then the S gates, because they didn't have a nice way of doing those otherwise, are also being done here by injection.
Mm.
So these are the main reasons that the performance would be worse in this factory is the magic state injection isn't post-selected. So you have like a 1e minus 2 injection instead of a 1e minus 3.
Mm-hmm.
Sorry, these are injections, not like ejections?
They're injection.
Did the things curl over in time and I'm not seeing it or something? How does this be?
It's hard to see. I'm sorry about that, but like there's basically like these little pointy bits that are touching. That's where the magic state gets injected, and then it grows out to meet the surrounding logical qubit that is the 2 holes to either side or the 2 poles to either side.
Okay.
That's how the T gate is achieved.
Yeah.
And after some decoding delay, it does the S injection to correct it or not.
Okay, so one way we can
wild.
think about, like, on the left, it looks like, wow, you need so many more qubits to get the same performance. That's because, we're not doing any post selection here.
That's a big part of the reason. Also, I mean, this little thing here is you can think of what this thing on the right is doing as performing a 15 to 1 distillation, but it's kind of running inside one color code and then turning into a surface code so that it's not only post-selecting, which gives it better performance, but it has the same distance. Like there's a sense in which they are basically doing the same thing, just in a different form, but obviously much, much, much more efficiently. Like the qubit count difference is completely insane and is even faster. I should point out, this is for a target error rate of 1 in a million. As you'll see, what you have to do to hit certain target error rates kind of changes qualitatively. So, for example, suppose we wanted to hit 1 in a billion, then this happens. So now here on the left, there are 15 copies of this, as well as 1 bigger copy. And you also have these things, which are actually S-state distillations of 1 layer, because that's what they were doing at the time. It turns out with the cultivation approach that we use now, we can get all the way to 1 in a billion. You just have to like try a lot more and be a lot more demanding about the cutoff that you'll accept. So you have to retry, like it takes like 6 times as many attempts. But you do eventually get there. And so here the size disparity has gotten even more insane.
You didn't improve the number of rounds, though.
No, that's right. So because we have to retry so often, these are back of the envelope numbers, by the way. Trust them to like 0.5 sig figs.
Nice.
Yeah, because you have to try so often, you have to try for about 300 rounds, whereas this only takes 200 rounds. But
It's quite a lot.
No, Alexi's really mad about that. About that time cost.
common
though, Craig.
mistake people make in papers is they overemphasize time when you could just like run 2 of them in parallel, and now it's 150 rounds per output.
Only 2 of them.
That's right, only 2 of them, and you get the same level of output.
So this on the right, this is the expected number of trials,
It's the expected number of rounds.
rounds.
So each trial in Magic State Cultivation might have a different number of rounds, like because there is some post selections that can fail early, some that can fail later. Some of them are based on the decoder, some of them are based directly on this detection event. You get a big variety of runtimes.
What is like the variance? Like if I think of this as like the expectation value of the number of tries.
In the paper, I have a plot that shows like the typical lifetime and how it drops off. Generally, what it looks like is it drops off initially. I don't know, you lose like 30% of shots for the distance 3 cultivation. Then to do the distance 5 cultivation, you might lose another 50% of shots compounding. And then it kind of tails off as you get into, I'm going to compute the gap. And then you get this big drop at the end when the gap comes in by like a factor of 10. So there is some structure to it. If we increase the target error rate even more to like 1 in a trillion, it turns out this factory is good enough for 1 in a trillion on its own. So it's sort of overkill for 1 in a billion error rate. But we are exceeding what we believe we can do with cultivation, at least with a noise strength of 1E-3. And so we have to start distilling on the right. And you see, I put like a Magic State distillation factory, but now it's a lattice surgery style one on the right. So the cubic count is drastically lower, mainly here again because of because there's only 1 stage of distillation instead of 2, and secondly because of the lattice surgery qubits instead of braided qubits.
What is the green cap?
Those are supposed to represent I either perform a Y basis measurement or a Z basis measurement, depending on previous things that happened in the factory. You can't tell what's supposed to happen from this. This is just like a thing I made in SketchUp. But there are rules behind it for how it works.
What is the tiny bit at the bottom? Is it the color code
These things?
getting?
These are the cultivations. So you cultivate the inputs into this factory
I see. So it's a single 15-to-1 factory
after.
after a
That's
full-
right.
I see. Okay.
But it's like it's because the noise is so high. Like if you went to lower.
Oh, sorry, it's not a 15-to-1 factory. It's an 8T-to-1 CCZ factory. Sorry, what were we saying?
I was asking if you went to lower noise, would it start to look more like the single?
Yes, absolutely. If you, for example, had a noise strength of 1E-4, then this would still be just a cultivation. And in fact, it would be shorter than this.
1e to the -4 in
Physical error.
Yeah, like gate error rate. So
In
they're very
1000
strong
or-
gate error
Yeah.
rate.
Okay.
2 cubic gate, basically.
Yeah. That-
Yeah, the CZ error rate.
What's the relationship between improvements in noise and improvements in the target and the single column?
Cultivation improves enormously as physical noise strength drops because it uses error detection. So here, this is like a distance 5 cultivation, which means it takes 5 errors lined up in the correct way that they leave no symptoms to make it fail. That means if you make the noise strength 10 times lower, you get that 10x 5 times. So you get 100,000 factor improvement. Additionally, because the attempt rate goes way down because you're failing less often, you could potentially cultivate up to distance 7 instead of distance 5 and get, even more of these factors of 10. Basically, I'm of the opinion that if we had a machine that had a 1 E-4 error rate, we would cultivate and that would be the end of it. We'd never do anything else. Like there'd be no distillation after for any computation anyone would ever really want to run.
You don't think you would Jevons paradox to someone asking you to cultivate
Yeah, maybe.
very nasty
Maybe our
states?
ambitions just grow to fill the space allotted. That's true.
You say that disappointedly, but I say that very excitedly.
Yeah, that's true. I should maybe be excited about that instead of resigned to. Like, oh my gosh, imagine the things we could compute.
Oh yeah, dude.
Surface code telescope achieved.
So true.
Okay, so this was like the surface code side of it, the requirements that we are asking for. These come down over time. I thought I would also mention the hardware performance coming up over time and improving. So eventually they'll meet in the middle. So like I said, 2014 was when Julian and the rest of the Martinez group did their rep code demonstration where they put 9 qubits in a line, they ran the rep code, they computed a lambda for it. And recently we put out this paper on the surface code doing the same experiment, but just with a surface code instead of a rep code. So we can compare these two things. So like this was a 9 qubit experiment on a line. You can maybe see that it would be very difficult if you tried to make a grid out of this as it is drawn. All that stuff had to be solved, et cetera, et cetera, et cetera. I don't know a lot about it. But 9 is less than 101 and 1 is less than 2. That I do know.
This device is so emblematic of this period.
I mean, yeah, this device was like the crowning achievement of that period. Yeah.
Yeah, there was a bunch of experiments.
That was like,
really
So I don't know. They don't do exactly the same benchmarking we do now, I don't think. So I'm not sure, like this C2 error, I think it might include single qubit gate error. I don't know if it's divided up in the same way. So I've just said it's like around 1% CZ error. They say in the caption of this figure that it indicates less than 1% CZ error, but to me that's like close to a 1%. I don't know. So the CZs have gotten a bunch better. Honestly, I think this probably undersells the improvements to the CZs, but I don't. Yeah, like I think there's a lot of other problems around it that get solved.
Is the one on the left single CZ, I think?
I don't know.
I feel like
I think that this is simultaneous.
simultaneous. Okay, because on the right, I know it's simultaneous, and this is a big deal. Is that it's all of them at the same time, and there is almost like no outlier. This is really like the big deal. At least
I was like almost everything that you show on the last slide made that CZ so much harder and so much worse. So the fact that it still got better is remarkable.
Yeah. And here we have the lambda plot from the two papers. So they, for the rep code specifically, so they had a lambda of 3 for the rep code. Now we have a lambda of 8, although saying there's a lambda of 8 when we have this noise floor, I'm not sure how I feel about that. But the noise floor is at least many orders of magnitude lower than what was achievable back in 2014.
if you crop the figure, it's fine.
Oh yeah, I'll just crop them.
Because it's trick, you know.
The least thing. Yeah, this I love that we can see these noise floors. And then here's the surface code comparison between 2024 and 2014. As you can see in 2014, and then in 2024, there's a lambda of 2 with 0.2% error per round. So if like
It's 2.1. You're
okay,
you're a bit
you're right here in the slide. It's 2.14 actually. Plus or
Yeah.
minus 0.02. Look, I'm clearly rounding.
I don't know. I really don't trust that.
Yeah. Yeah. In 10 years, we're not going to care. Like, yeah, it was 2. I don't know. I look at like the improvement from here to here, and
you are expecting. Wait, can you go back? So factor 2 point something. So lambda 4
Well,
here. Is it?
it's not really this improvement, although that's nice. It's more this improvement from 1% to 0.0000001%.
But yeah, Yeah, okay, I agree.
where you go from like, oh, it lives, 100 microseconds.
Yeah,
to
yeah.
It lives like seconds or.
But this is
I think I was saying we're not gonna
gamma,
like
no
we
longer.
didn't really pump lambda, but we really pumped the distance.
Yeah, it's just that no, it's like you have something that is so much bigger.
That is the
Without
that
ruining
is
the
the
lab.
original Austin Fowler promise to the experimentalists,
Yeah.
right?
Scale.
Just pump the distance.
just scale up
Yes.
more qubits.
Yeah.
On a square lattice.
Yeah. So obviously the hope is that both in the error correction and in the hardware, we see the same improvements over the next 10 years again.
I was about to be like, I'm really excited to see this slide, like for the
Yeah.
2024 to the 2034. But also, if we only have a lambda of like 6 in 2034, I'll be sort of embarrassed.
Yeah, it is true that I think the hardware,
Yeah, the like next 10 years.
Yeah.
the hardware ambitions in terms of the qubit size are definitely outsized compared to the hopes for the logical improvement. But we can compete to see who can improve things more. Anyways, that's my last slide. I mean, I guess technically I have a skip slide here about improvements to like our options, but I like the slide, but I felt like it didn't fit anywhere.
As the person represented on this slide, I also like this slide. Like,
The unrotated versus rotated was in 20.
No, that was just what was available. That
Okay.
was when it was found.
Okay.
so actually, wait, yeah, it was rotated was available, but not being used in the defect diagrams.
As far as I know, I don't know why they weren't, because I mean, this is another thing where like
Not anymore.
nowadays, this is what we're familiar with. It's what we would
Yeah.
pick first because it's better. But back then, like you can find papers from the past 2 years where people try injection, but with a rotated surface code instead of an unrotated surface code. And it's clear from the framing of the paper that they were worried it would break. But like, why would it break? I don't know.
It's a good question.
Yeah, does anyone have any questions or comments?
No, it's very cool to see over a whole decade what happened.
Yeah, the decade really does help to make it clear because like year to year, you see improvements, but you also see like backtracking on this in order to improve that.
It's also kind of cool that 2014 was like at the same time that Austin was, I don't know, advertising this like glorious plan, was also the same time that the last.
I would say
rep code stuff.
that's not so much a coincidence. Basically, you're saying when they did this experiment, Austin gave a talk in the same year.
That's actually true. That's fair enough.
Yeah.
Well, and that it was exactly 10 years before now.
Yeah. It's maybe the nice thing is that in the talk, he included this nice summary slide, which is a very Austin thing to do. Yeah.